Okay, good evening, ladies and gentlemen. This is Professor David J. Del Reyes. Okay, I am here in Los Angeles, California. My topic for tonight will be a long video format. This is a continuation of my topic of AC machines, and this is with regard to the topic parallel operation of single phase alternators. Okay, let's proceed. So this is actually a lecture for my viewers in the age bracket 45 to 54. I hope those young ones would like also to watch my long video format and AC machines. Okay, but this is most especially dedicated to the age group 45 to 54 up maybe. If the young ones would like to watch it, it's better for you guys. Okay, let's proceed. My subject matter for tonight will be AC machines, and this is lesson number 69. Okay, and the title of the topic will be problem on alternators which are connected and parallel. So we are given two alternators. They are connected in parallel, and in parallel with them is actually a common load designated by Z sub L. Oh, this is a switch. Of course, this is a switch. The problem here is the so-called computation of the circulating current. Circulating current. Hold on. I'll get my wrist. One of the most important aspect of parallel operation is the so-called circulating current. There come a time that the alternators are actually operating in parallel and the load is disconnected. Okay? So if this is running and this is also running, whether we like it or not, there should be a circulating current in here. Right? If this voltage here is greater than this, of course the circulating current will be in this direction. That's the circulating current. But just in case this voltage here is greater than this, meaning in magnitude, the circulating current will be in this. That's the circulating current. And the problem is asking what are the values of the circulating current. Okay? And what's the significance of the circulating current? The circulating current is actually a very big value if there is no load connected across the alternators. And this big current here might, okay, burn the armature windings. Okay, so we must have to determine the so-called worst case scenario just in case the load is disconnected and this is operating, and so with this there will be an instantaneous circulating current that will circulate on the circuit and might burn one of the alternators or both alternators maybe. So it's a must for design engineers that we know the so-called value of the circulating current just in case the load is disconnected accidentally or unintentionally. Okay, let's proceed with the problem. Two single-phase alternators, I will try to read the problem, are connected in parallel and operating without load. This is without load. So no load here. The load here was removed without load. Calculate the circulating current in the windings, meaning in the armature windings. Okay? Because the alternator, there will be an induced voltage on the armature windings, but just in case there come a time that the load will be disconnected, the current passing through the armature windings will be the current due to the impedances of alternator number 1 and number 2. And these values here are actually very small. Okay? if we try to compute for the circulating current, it will be voltage all over a small value. If the numerator is small, of course, this should be very high. Okay, and this very high value of circulating current is actually very dangerous. So it might burn alternator number 1 or alternator number 2 if their current ratings are actually excellent. Okay? Okay, let's try to bring out the unknown. When E sub 1 is equal to 230 angle 0 degree and E sub 2 is 230 angle 30 degrees, they are displaced 30 degrees apart. The problem is asking what will be the value of the circulating current. Okay? For the first unknown, this is the first voltage, the voltage across this, and the voltage E2 will be this. Okay? The problem is asking what will be the circulating current. Of course, E1 is greater than E2, so for the first unknown, the direction of the circulating current will be to the right. It will go like this. Okay? Next question. When the value of E sub 1 is 230 angle 0 degree and E sub 2 is 200 volts angle 180 degrees, they are all out of phase. What will be the value of the circulating current? We just wanted to know the value of the circulating current if these are the specification of the voltages. The first one, they are 30 degrees out of phase. The second one, they are actually out of phase 180 degrees. That is, the first one is this one, the second one is this one. This is actually E sub 1 and this is E sub 2. With this given condition, what will be the value of the circulating current equal to? Okay? Okay, I will try to erase this one so it looks good. And so with this one. Okay, let's try to bring out the solution of the problem. The problem is just a straightforward thing. It's just a basic knowledge of the so-called equation. Voltage is equal to the product of current times impedance. For alternating current machines, which applies to alternating current machines, voltage is the product of current times impedance. So in here, we are just solving for the current, so it should be voltage over impedance. Okay, but this voltage here should be the so-called net voltage. And this one should be the total impedance, total Z. Okay, so to compute for the circulating current on the first unknown, we must have to compute for the net voltage all over the total impedance. We are given the value of Z1. It is this value here. Impedance, internal impedances of transformer are actually small values. Okay, very small. And if the impedance to the circuit is very small, the circulating current that will come out will be a very big value. And Z1 is also given. It is also 0.025 plus J.06, meaning the internal resistance of alternator number 1 is 0.025, and so with alternator number 2. And the inductive reactance is, they are both 0.06. This is 0.06, this is 0.06. So if we try to compute for the current circulating, we must have to take the sum of Z total. Z total, Z1 and Z2, when the load is disconnected, they are in series. So it will just be simply C1 plus C2. Since the impedances are already actually in the so-called rectangular form, that's an easy one already. 0.025 plus G.06 plus 0.025 plus G.06. This is actually with the quantity, right? But since the operation is addition, we are safe to remove the quantity. Okay? So 0.025, 0.025, we add the real part to real part, that's 0.05. The imaginary part are the terms with the J sign, 0.06 plus 0.06, that will be 0.12. And if we try to convert this to the so-called polar form, because this is the overall real part, this is the overall imaginary part, but in the computation of the current, we must have to use the total value of the impedance. We don't just divide the net voltage by the resistance or by the reactance. It should be by the absolute value of the impedance. And in here, it seems we are given the resistance, and this is we are given the reactance, so this will be the impedance. This is J, this is R, this is Jx of L. In the computation of the current, we must have to use this value here, the value of the hypotenuse. We know the value of this, we know the value of this, and if we try to compute, it will be 0.13. The angle of inclination here is 67.30 degrees. For the meantime, we do not need the angle. We are just interested in the magnitude. So the magnitude of the impedance will be 0.3 ohms. Okay. What will be the net voltage on the circuit? The net voltage on the circuit, this is 230 angle 0 degree, and this is 230 angle 30 degrees. Okay. If we try to draw the vector diagram of this one here, the real part of this one is bigger than this one. Right? So supposed to be if this will come out, and so with this, they will try to fight out each other. This should be stronger than this one, so the circulating current will be to the right. So in here, I place it here, E1. Okay, the net voltage will be the difference E1 minus E2. Okay? It will be something like this. So you could visualize it. My figure is very small. E1 is this one. This is 230. This is E2. This is also 230, but this is with an angle of 30 degrees. They are out of phase. The angle between E1 and E2 is 30 degrees. But we are subtracting, right? So this is plus 230. So if we try to take the reverse of this, we go to this direction. This is actually minus 230. Okay? And if we try to take the vector sum of this plus this, we use the so-called parallelogram method. Okay? So this should now be the net voltage. And this should be the resulting angle. Because 230 angle 0 minus 230 angle 30 degrees, we take the reverse of this, right? So it seems this is gone. So actually we are adding two vectors. This is negative 230. This is plus 230. Of course, this should also, this is 30 degrees because it came from here. It is 30 degrees. Okay? And if we try to take the vector difference of this one, this 230 is just 230 plus G0. It got no vertical component. And this one here, it got a vertical component. This is minus 230, right? It got a horizontal component and it got a vertical component. This is minus and this is minus. So it will become minus of in quantity 199.18 plus G115. So they will become both negative. Negative 199.18 and this will be negative G115. Okay, this is negative. So that's a negative 199.18. This will fight with this one. So 230 minus 199, it will come out to be 30.82. This is 199, this is 230, so the difference is actually 30.82. This is still bigger. That's why I told you a while ago, the current should go to the right. And the imaginary part, it's negative, it's downward, right? It's a negative J115. So actually, the resulting voltage will be something like this. The real part is plus, the imaginary part is minus, this is 30.82, this is J115. So if we try to get the net voltage, it should be the vector sum of 115 plus 30.82. Okay? And what will come out will be 119.058. The angle is, this should become 75 degrees. For the meantime, we do not need the angle. We are just interested in the value of the absolute value of the magnitude. So the absolute value of the net voltage for case number 1, for the first unknown, it will be 119.058 volts. So by using the equation voltage equal to IC, I now will be voltage over C. Of course, this will become the net voltage. It will be 119.058 over 0.13. The total impedance magnitude is 0.13, right? So absolute value of the circulating current for case number 1, for the first unknown, will be the absolute value of the net voltage over the absolute value of the impedance, 119.058 over 0.13. And it will come out to be 915.83 amperes. This is a very big current. Okay? So this 915 might be bigger than the current that will come out from generator number 1 or number 2. So the worst case scenario, okay, if the load is disconnected, this might get burned and this might get burned because this is very big. Okay? Or case number 2, the net voltage will be, the voltages are actually, it is this one. The first one is 230 and the other one is 200. They are out of phase. The first one is at 0 degree, right? The other one is at 180. Okay? This is the first voltage, this is the second voltage. They are both horizontal. So the net voltage will be the value of the bigger minus the smaller, which is bigger maybe. So it will be, the operation here will be plus, okay? Okay, so it will be 230 angle 0 degree plus 200 angle 180 degrees. This is at 0 degree, this is at 180. 230 plus G0, it got no vertical component. This 180, it got no vertical component also. It's a pure horizontal voltage. This is a real voltage, this is a real voltage. So it seems this will now become negative 200. This is minus G0. This is plus G0. I got nothing in it already. It's nothing. So what will come out will, the net voltage will just be simply a pure real voltage. It should be the difference between the bigger minus the smaller. Right? 230 minus 200. Real part, so it will be 30. So the net voltage for the second unknown will be a 30 voltage going to the right. This is 30 volts. And the angle is at 0 degree. 30 volts, angle 0 degree. So the absolute value of the net voltage for the second unknown circulating current will be 30 volts. Still, the absolute value of the impedance is 0.13. So the circulating current for case number 2, for the second unknown, it will be 30 over 0.13, and this should be 230.77 amperes. This is still a very big current, which might burn alternator number 1 and number 2. Okay, why? How come this is smaller? Because the voltages for the second unknown, they are out of phase. The first voltage is to the right, the second voltage is to the left, right? So real part, which is bigger, it should be bigger minus smaller. That's the net voltage. On the first case, it is something like this. Okay, then we take the negative equivalent. So the resulting vector sum will be by using the parallelogram. It is like this. So the net voltage is actually bigger. 119.08. This is 119.08. Okay, this is only 30. So by the same denominator, this is 0.30, this 0.30, this should be bigger. So the first unknown is 915.83 amperes. The second circulating current is 270 or 230.77 amperes. What's the importance of this problem here? Okay, for design engineers, they should know the worst case scenario just in case the load is accidentally disconnected or just simply disconnected. Because if the load is disconnected and both alternators are running, okay, there will be a big circulating current which might burn the armature winding of alternator number 1 and number 2, and we want to prevent that one. That's economy. Okay, that's it, guys. So for those in the age bracket 45 to 54, this is for you guys. Okay? If you would like to subscribe to my channel is at youtube.com/@proofdavidj3. If you want to share it, please click share. For those young ones, if you would like to watch my long video format at Easy Machines, you could watch it. Okay, good evening from Los Angeles. Professor David J.